So, how do speed cameras work? You have two cameras placed a known distance apart from one another. The first camera starts the timer, and the second camera stops it. Now, average speed is defined as the total distance traveled over the total time taken to travel that distance. In this case, it's 20 meters per second. And this is one criticism of speed cameras. If you have another car, which is traveling at the speed limit of 20 meters per second, the red car can travel as fast as it likes for one particular section of the journey and then slow down so that it has the same average speed as the blue car. Now you can also calculate average speeds of a distance time graph. So if you have any general distance time graph, as one that is being sketched out here, you can take any 2 points on that distance time graph and draw a line between them, and then the gradient of this line will be equal to the average speed of the object. And this method also works if you want to find out the average speed between any two other times. So for example, between 1 and 4 seconds. Because you're still calculating the total change in distance over the time taken. Now what if you don't want the average speed? What if you want the object's speed at a particular moment in time? For that, you need to calculate instantaneous speed. To do this, we start off like we're calculating average speed, but then we bring the points closer together so that we represent a very short time interval. Eventually, the line approaches the tangent to the curve at that point, and the gradient of the tangent at that point represents the instantaneous speed for that particular time. Now, even though this vehicle has an average speed of 20 meters per second, you can clearly see that speed at particular moments in time exceeds the speed limit. If a distance time graph has a gradient of 0, then the speed is also going to be equal to 0. Now for a distance time graph with a constant gradient, both the average and instantaneous speed are equal to the gradient of the graph. But now speed doesn't really tell us anything about the direction in which the object's moving. So we need velocity for this. Velocity is a vector, it has magnitude and direction. The average velocity is defined as a change in displacement over the time taken to achieve that change. Now you can think of velocity as speed in a particular direction. It uses displacement instead of distance. So what's the difference between distance and displacement? Well, just like velocity, displacement is distance in a particular direction. Take two towns, A and B. Now the blue curve represents any roads or path you can take to get from town A to town B. The red line represents the shortest straight line distance from one town to another. Now even though the roads you can take can change and they can vary in distance, there's only one displacement. Now take a triangle. The two blue lines represent the roads from A to B, and the red line represents the shortest straight line distance from A to B. Now the total distance we travel if we walk along the blue lines is 3 plus 4 kilometers, which gives us a distance traveled of 7 kilometers. Now for the displacement, we would say that the displacement of B from A, we would say that the displacement is 5 kilometers on a bearing of 0.53. Now even though to travel from A to B, we've taken a road north of 3 kilometers and then a road east of 4 kilometers, when we calculate the distance, this information is lost. We only know that we traveled a total of 7 kilometers, but we don't know the direction that we traveled in. But the displacement also allows us to get a direction. Now I can illustrate this idea of displacement and velocity using a displacement time graph as well. Now when you have a constant positive gradient, you have a constant positive velocity. When the gradient is 0, just like in a distance time graph, for a displacement time graph, the object is also stationary. And when the gradient is constant and negative, you have a negative velocity. So that means the object is returning to its starting position. So the displacement of the object, measured from its starting point A, is 0. Now when you have a tangent to a distance time graph, the gradient of the tangent is equal to the instantaneous speed. In a similar way, the gradient of the tangent to a displacement time graph is equal to the instantaneous velocity. Now acceleration is intuitive. Now by looking at this animation, you'll see that the red car has a greater acceleration than the blue car. But how do we quantify this? Acceleration is defined as a change in velocity over the time taken for that change. Now acceleration uses velocity instead of speed because we want it to be a vector quantity. A positive change in velocity means your object is accelerating, and a negative change in velocity means your object is decelerating. Now you can calculate acceleration in two ways. You can calculate it using the formula or a velocity time graph. Now for velocity time graph, the gradient is equal to the acceleration because acceleration is equal to the change in velocity over the time taken for that change, as we saw earlier. And the steeper the gradient, the greater your acceleration. Now going through some examples for a velocity time graph, if you have a constant positive gradient, you have a constant acceleration. If you have a graph with zero gradient, that means that there is no change in velocity over time. In other words, you have constant velocity and zero acceleration. Now if the gradient is negative, you have a negative change in velocity over time, meaning constant deceleration. Now if you have this graph, you might be tempted to say that the object is decelerating. But in this case, as your positive gradient is getting smaller, your acceleration is also getting smaller over time. So you can say that your acceleration is decreasing. Each of these bars represent a small change in displacement, delta s. Now, delta s is approximately equal to v, the velocity, times the small interval of time, delta t. Now, this is an approximation because over a finitely small interval of time, the velocity is going to change somewhat. So as we make the interval of time delta t smaller and smaller, this approximation becomes more exact. And since each of the bars represent an area under the graph, which is equal to the change in displacement, if we add up all these small areas, we're going to end up eventually with the total displacement, which is equal to the area under the velocity time graph. Now, this is a relatively basic topic to cover using animations. On this channel, I'm going to be covering more physics animations that will make physics more intuitive and easier to understand. So please subscribe if you're interested.